Hey guys. So today I want to talk to you about absolute convergence and the root and ratio tests. So for the last two convergence tests, we're going to learn for infinite series. And it's the last bit of material that's going to be on exam 1. Or sorry, exam 2. I'll give a few minutes for folks to show up. I just posted that link a couple minutes ago. Before we get into it, I want to give a little breakdown of the exam. Oh, weird. On the 15th. Okay. Yeah, I see. It's funny. I thought that was there. I even updated the thing, but yeah, it's not. Okay. So here, let me paste it in. All right. So the link to the lecture from last Wednesday, 7:15, is up now. I went back and updated the announcement, but I apparently I just didn't paste in the link. But it's there now. So this is now present. My computer did a forced restart just a second before we started here. So I gotta pop this back open. Yeah, thank you for letting me know. All right. Okay. So your exam 2 is this Friday. The topics that we're going to cover, I'll break them down by section, are improper integrals from section 7.8, sequences from 11.1, and then our basics of series, which are like partial sums and the definition of series and stuff, and telescoping and geometric series from section 11.2. 11.3 will be on there, which is the integral test. 11.4 are the comparison tests. 11.5, which is on alternating series. So the alternating series test and estimation theorem. And I want to give a shout out to Thomas, who sent me a really neat animation for the estimation theorem proof that I'm working on to try and improve into something that's a little bit more general. But that's awesome, and thank you, Thomas, for that. I really like that, made my day. The last thing that's going to be on the test here is 11.6, which we're going to talk about today. This is the root and ratio tests, and the concept of absolute convergence, how it relates to what's called conditional. Convergence. So I actually mentioned last Wednesday what it means for a series to converge conditionally, but I want to be a little bit more specific. I will try to find time to do a few homework problems today, but tomorrow, Wednesday, will be our review day. So definitely, I'll try to get through a couple here during lecture. If you want, we can do more during the office hour. And then our next class meeting will be dedicated all to solving problems. Before we do that though, I need to introduce this material because we didn't get a chance to talk about this last Friday because I couldn't meet last Friday. So let's talk about section 11.6. It's titled the root and ratio tests. And absolute convergence. The first thing we need is a definition. The series sigma an, sum from wherever, I'll say from 0 to infinity, is said to be absolutely convergent if the new series sigma n from wherever to infinity of the absolute value of an converges. So this is what we mean when we say absolutely convergent. This is what it means for a series to converge absolutely. If when you swap the original terms of the series for their absolute values and then add up that new series, you get one which is convergent. Say the original series was absolutely convergent or converged absolutely. There is a theorem that says if the absolute value series converges, so does the original. In other words, absolute convergence implies convergent. If you converge absolutely, then you converge in the traditional sense as well. This is really an extension of something called the triangle inequality. This comes from, I don't want to spend too much time on the proof, but I'll give a quick proof sketch. I could talk about this shit for days. Basically, analysts, mathematicians who do the sort of stuff we're doing now for a living, are concerned with mathematical spaces called metric spaces. A metric space is a collection of mathematical objects where you can define a concept of distance in a way that makes sense. So we're normally thinking of what's called the L2 metric, the Euclidean metric, the metric that takes the straight line distance from any one point to another point and calls that the regular distance. You could also define what's called the L1 metric, where you take the, imagine it's a network of roads all laid out on a grid, the grid distance, where you go over and up. The L2 metric, the L1 metric, there are others. What makes a metric, what makes a distance function a reasonable distance function is that it satisfies a few criterion. Right, that's it, yeah. So what Lucas just typed there is the triangle inequality. It says that the absolute value of the sum of two numbers is never any larger than the sum of their absolute values. This needs to be true in any metric space. This is one of three things that we require to be true about a distance function in order for it to be a distance function. So the triangle inequality can be extended to saying if you add up not just two things, but three things or even n things, but that is always less than or equal to what you get when you take their absolute values separately and then add. So this means that sigma n from wherever to say capital N, if you take the whole thing in absolute values, that's less than or equal to sigma from wherever to capital N with the absolute values inside. This is this, this is this. And since this is smaller than this is smaller than this. All right, really saying the exact same thing, just here in sigma notation. So then if you send n to infinity, you get this. If this is finite, we say sigma an converges absolutely, because this is the series that's involved in the definition of absolute convergence. And since this is bigger than this by dct, if this guy converges, so does the absolute value of sigma an, which means the only way for your absolute value to be finite is if this is finite and that's the proof. Right, if you want to be rigorous about it, then you need to talk about this in terms of partial sums, but really we've done that. So this says that the nth partial sum of the series with absolute values on the outside is smaller than the nth partial sum of the series with absolute values on the inside. Therefore, if this guy converges, this guy converges. And that's by dct, using this inequality. So if you converge absolutely, you converge in the old-fashioned way. And sometimes the easiest way to solve a problem is to show that the series converges absolutely, and then deduce that the series converges in the traditional sense. Okay, so I want to give some answers to questions appearing in the chat. Ryan asks, do we need to know the proofs of all the theorems for exam 2? No, you don't need to know the proofs of the theorems, but you do need to know how to use the theorems. You will be writing your own proofs using the theorems, but not proving the theorems themselves. So when you use limit comparison test to show a series converges, you're proving that that series converges, but you're not proving that the limit comparison test is true. You're using the limit comparison test to prove that the series converges. So you are writing proofs, but you're not proving the theorems that I give you in class. And you don't need to know the proofs of the theorems from class. I just show those to you because that's how you understand the theorems. You understand why the theorems work if you understand why they're true, right? And understanding why something is true is really proving it. Gustavo makes a note here that this is kind of similar to 11.4. Yeah, when I say this part right here, I am using 11.4. 11.4 includes the direct comparison test. So the proof that absolute convergence implies convergence relies upon the machinery of section 11.4. That's very true. Okay, so what comes next? So make sure you have this definition and this theorem nice and clear in your notes. Very, very important. I'm going to tuck the proof of the theorem underneath here because that's not as important for your notes. If you didn't catch it, just rewatch the video and you can fill it in, maybe leave some space in your notes if you need it. But the next theorem is called the root test and the ratio test. So I'll do the ratio test first. Most people like the ratio test a little bit more than the root test. Root test is easier to prove. So here's what the ratio test says. Given a series S equals sigma n from wherever, I'm going to say 0, but it could be from anywhere else, an, calculate L as the limit as n goes to infinity of the absolute value of an plus 1 over an. 3 cases. If L is less than 1, then the series S converges. Not just that, but it converges absolutely. If L is bigger than 1, then the series S diverges. And if L is exactly equal to 1, the test is inconclusive. So this is called the ratio test. The reason we call it the ratio test is because you're calculating a ratio of consecutive terms. So an plus 1 is the term in your series that comes right after an. If the sequence an that is being summed in this series, if the an's themselves are decreasing, then an plus 1 is always a little bit smaller than an. If these an's are decreasing really, really fast, then an plus 1 is considerably smaller than an. Small enough so that as n goes to infinity, that limit will be less than 1. And we know that these guys decreasing really, really fast to 0 is precisely what's required for the series to converge. Not just going to 0, but going to 0 hella fast. This measures how fast the an's are decreasing. If they're decreasing fast enough so that this limit is less than 1, then the series is not only guaranteed to converge, but guaranteed to converge absolutely. That's a big deal. On the other hand, if this ratio has limit larger than 1 and the series diverges, that means either the ANs are not decreasing in the long run, or they're not decreasing fast enough. And if L equals 1, if these guys are pretty close to each other, either the ANs are decreasing but not fast enough, or non-decreasing, then the test is inconclusive. So the ratio test is one of the most useful convergence tests we have. And as we move out of this section, exam 2, to start talking about power series, it will be the most common test that we use. But for now, it's just one of like the 6. Okay, I got one more for you. And that's the root test. The root test looks a lot like the ratio test. Only instead of a limit of ratios, you're going to take a limit of roots. So given a series, S equals sigma n from wherever to infinity an, calculate capital L as the limit n to infinity. What you do is you take the absolute value of an and then take the nth root of that and send n to infinity. So the nth root of the absolute value of the nth term, and then send n to infinity. And then the rest looks the same. If L is less than 1, then S converges absolutely. If L is greater than 1, then S diverges. If L equals 1, the test is inconclusive. So you see they're very similar. The ratio test is really nice in series that have a lot of factorials or factorial-like objects. The root test is very nice in series that are like almost geometric. I want to make a note. A common limit in root test stuff is the limit as n goes to infinity of the nth root of n. This is lim n to infinity, n to the 1 over n. So that's like infinity to the 0, which is a problem. This is an indeterminate power. You can go through the work. This limit is equal to 1. So you don't want to go through the work every time you need this limit. You should go through it once. The way you do it is by taking natural logs. So this is because the natural log of n to the 1 over n is 1 over n times the natural log of n. So lim n to infinity ln n to the 1 over n equals dot 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 equals lim n to infinity 1 over n times log n, which is lim n to infinity log n over n, which by L'Hopital's rule, right? Because if you plug in infinity, the top and bottom both go to infinity, so you can use L'Hopital's rule. This is lim n to infinity 1 over n divided by 1, which is 0. Therefore, so the natural log of n to the 1 over n goes to 0 implies n to the 1 over n goes to e to the 0, which is 1. This is an e. As n goes to infinity. So yeah, so the limit of the nth root of n, or the limit of n to the 1 over n, that's 1. And you don't want to have to show that every time because it's a bit of work, right? It involves taking logs and using L'Hopital's rule. Another note, another common limit is the limit as n goes to infinity of 1 plus a over n raised to the bn. This is always going to be, I've shown you this once before, e to the ab. You prove it the same way, right? You take natural logs and you juggle things around and use L'Hopital's rule, and then eventually at the end you exponentiate. You should prove both of these, right? You should prove this on your own. Then use it freely. If you take the time to prove this e to the ab limit on your own, you'll remember it. And I don't require you go through and show work for this particular limit on the test. If you want to use this limit on the test, just use it. Don't take the time to do the L'Hopital rule, natural log, all that shit, because you'll run out of time. There's nowhere near enough time to do this every time it comes up. So you should prove it once, like today, and that way you'll remember it. And then when it comes to the test, you can just use it every time something like that shows up. Same thing here. Go through this argument carefully once on your own, make sure you really understand it. And that way these two boxed special limits will stick forever in your brain. They will be yours, no one can take them away. And as you need them on the test, you will not need to hesitate. So let's come back down here. I'll show you the statements of the root and ratio test, in case anybody needs to get those back in their notes. And then I'll show you some examples. I also like to go through a quick proof of the root test. It's easy to prove. I'll give just another few seconds here for anybody who's still writing. Any questions about the statement of the theorems? What they're saying or how we might use them? Okay. So, there's some paper I haven't abused yet. A quick proof of the root test. So I want you to see why this works. It's kind of like the limit comparison test has a nice intuitive proof, the root test has a nice intuitive proof. And then usually you use the root test to prove the ratio test. So if you pick up a real analysis book where they treat these things very carefully, what you'll do is you'll prove the comparison tests and some results on geometric series, then you prove the root test, and then you use the root test to prove the ratio test. In fact, root and ratio tests are equivalent. The number L you get out from the root test is always the same as the number L you get out from the ratio test. That's a fun fact that's hard to prove. But let's suppose S is sigma AN, sum from wherever to infinity, has limit, has root test limit L equal to lim n to infinity nth root abs an smaller than 1. This means that for large n, or very large n, L is approximately equal to the nth root of the absolute value of an. Which means L to the n is approximately equal to the absolute value of an. All right, I just take this statement and I raise both sides to the nth power. The nth power of the nth root of an is just an, and the nth power of L is L to the n. So now if you sum those sums should be approximately equivalent. Or if you're being really careful, you would say n from cap n to infinity, right? Because we're talking about tails of series, just like we did when we talked about the limit comparison test. The series on the left, this is a geometric series. With common ratio r equal to L. And we assumed L is smaller than 1. Now L is necessarily positive because of how it's defined. L is a limit of an nth root of an absolute value. So 0 is less than L is less than 1, which means the absolute value of L is less than 1. So the geometric series converges. Since this guy is approximately equal to this guy, and this guy has to converge, this guy has to converge. Pretty slick, right? So the root test actually makes a lot of intuitive sense. It turns out that the root test is usually a little bit harder to use than the ratio test. Because the nth root of an is often a little tricky to calculate, but it works out nicely. And I think the intuition behind the root test is very good. So let's see how to use this. I did see a question in chat there. It seems like a test of convergence. We're looking at the behavior of the fx and function. Nicholas, could you clarify a little bit the comment in chat? So definitely what we're doing is we're looking at the tail of the series, and we're saying that the tail of S has to be similar to the tail of this geometric series. So if the geometric series converges, S converges absolutely, right? If this series, so this series must converge, and then I'll be a little bit more specific. If this converges, then the original series converges absolutely. So if the series has root test limit smaller than 1, then that series converges absolutely, which is what we wanted to prove. the argument that if L is bigger than 1, the series diverges goes very, very similar. Just here, I'd say L is bigger than 1, so the geometric series must diverge. If L is equal to 1, then it's inconclusive. That's a little bit more subtle, but the main thing here I wanted to prove is that if this limit is smaller than 1, then this series converges absolutely. And that follows pretty neatly from this. Again, the proofs of these theorems, you don't need to know them by heart or anything like that. I just show them to you so that you might understand a little bit why the theorems work. But the main thing we care about, especially with a test coming up, is that you know the theorems and you can apply them. So, one more definition. A series which converges but does not converge absolutely is called conditionally convergent. And there's a pretty wild result due to Riemann, the same Riemann from Riemann sums, that says if you take a conditionally convergent series and you reorder the terms, you can actually get that series to converge to whatever you want, which is strange. You can even reorder the terms to make the series diverge. So if a series converges but doesn't converge absolutely, think like alternating series, like the alternating harmonic series. That's a very weak form of convergence. The convergence is usually very slow. And if you get in there and start fucking around with the series, you can make it diverge. Very, very weird stuff. So let's leave it at that. This is called the derangement theorem. You can rearrange or derange, funny terminology, the series, dearrange, to make the series appear to converge to whatever you want. And this is one of the harder theorems to prove in like an advanced calculus class, undergraduate real analysis. But we're definitely not going into that. The idea that we need is just the definition of conditionally convergent. So a series that converges but doesn't converge absolutely. For example, the alternating harmonic series. This converges by AST, the alternating series test. We did this last Wednesday. However, if you swap the inside for its absolute value, what you get is I've got the negative absolute value of -1 to the n plus 1 over the absolute value of n, right? Absolute values play nice with multiplication and division. So I can give the absolute value to the top and the bottom separately. And then the absolute value of a power is the power of the absolute value. The power and absolute value also commute. This is sigma n from 1 to infinity 1 over n, which diverges. It's the harmonic series, or it's a p series with p equal to 1, which is not bigger than 1. So the original series here, plus we say sigma n from 1 to infinity -1 to the n plus 1 over n converges conditionally. If the absolute value version converged, then we would say that the series converges absolutely, but the absolute value version diverges. So the original converges, it converges by the alternating series test. We went through that before. but the absolute value version diverges. So you converge, but you don't converge absolutely, which means you converge conditionally. Right? That's what conditional convergence means. There's pretty much always a question on my exam 2 where I give you some series and I ask you to classify them as conditionally convergent, absolutely convergent, or divergent. Those are the 3 possibilities for a series. Diverging, converging absolutely, converging conditionally. And you need to be comfy classifying series like that. So let's do something like that. Let me grab some examples from your textbook. Y'all are down here. Absolute convergence. So here's the alternating harmonic series. Oh no, it's not. It's something else. Let's look at something a little more fun now. Root ratio test. Just some problems. Okay. How's about divergent? Use any test to determine whether the series is absolutely convergent, conditionally convergent, or divergent. Okay, let's look at like 32 and 34. So I'll write this down and then I'll go back to the dot cam, classify as abs convergent, conditionally convergent, or divergent. And I'll write down a few of them. We'll look at 31 also. So 2 to infinity, negative 1 to the n over the natural log of n. I'll call that S. I'll call T the next one, sum from 1 to infinity, parentheses 1 minus n over 2 plus 3n, all to the n. It's called Q. Sigma n from 1 to infinity, negative 1 to the n, inverse tangent of n, all over n squared, and R. We'll call him the alternating 1 over n log n series. Okay. So, can we classify the series QRS and T as absolutely convergent, conditionally convergent, or divergent? Let's start with S. What test would be good to start playing around with the series S? Sorry, this is a negative 1. I see that's not showing up on the dot cam very well. Negative 1 to the n. So how would you start playing around with this guy? This guy. I'll write out the first few terms while you're thinking. This is 1 over the natural log of 2 minus 1 over the natural log of 3 plus 1 over the natural log of 4 minus 1 over the natural log of 5, and so on. What kind of series is this? Good. Sorry, yeah, my chat's being a little silly. Oh yeah, actually, it looks like I missed a bunch of things from you guys. All right, let me back up a little bit. How does n through an equal to L? So Coming back to Simon's question in chat at 12:07, how does the nth root of an equal L to the n? It didn't. L was the nth root of an, which means L to the n is an. So if x is the nth root of y, raise both sides to the nth power, x to the n is the same as y. So if you look back through that, I think you'll see it pretty well. I just raised both sides to the nth power. That's answer to Simon's question. Nicholas says the base function I would assume would go to 0 or close to it, so from the definition was less than 1 with observation. Yes, so Nicholas, you're saying that you're considering the related function, the function that's related to the sequence an, and that it would have to go to 0. That's true, but remember what we were looking at there is ratios. So it's not whether f of x, or that function, goes to 0, it's whether f of x plus 1 over f of x gets smaller than 1. So going to 0 isn't enough, and the ratio test doesn't look at what an itself does, it looks at what the ratio of consecutive terms do. So an plus 1 is the term that comes right after an. So if an plus 1 is smaller than an, then an plus 1 over an is less than 1. And the question is, in the limit, as n goes to infinity, does the next term stay smaller than the term before? Being a little bit smaller isn't enough to guarantee that the limit will be less than 1. And I'll show you some examples of that in a second. But remember, it's not the function itself, or it's not the sequence itself, it's a ratio of consecutive terms. The algebra that I did in this previous example here, let me come back and take a closer look at that because I see a few comments there. We need to remember the algebra of absolute values. So the big stuff here is this. The absolute value of a ratio is the same as the ratio of the absolute values. And an absolute value of a power is the same as the power of the absolute value. So -1 to the n plus 1 over n, all in absolute values, if we break this down one piece at a time, is the absolute value of the top over the absolute value of the bottom. That's using this first rule. The absolute value of n is just n because n is running from 1 to infinity. The absolute value of the top, now I use this second rule to say that that's the absolute value of -1 all to the power n plus 1. But the absolute value of -1 is 1. So this is 1 to the n plus 1 over n. And 1 raised to any power, as long as the 1 is actually a constant 1, is just 1. So those are the steps there. These two rules you need to be comfy with. In addition to that, you really want to be comfy solving absolute value inequalities. But we'll talk more about that later. If there's a third rule for absolute values that you need, it's that it's multiplicative. So the absolute value of A times B is the absolute value of A times the absolute value of B, and sub-additive, i.e. the triangle inequality. So the bracketed blue statements here are the important facts about absolute value for this class. Okay. So, coming back here. Coming back here. It's not geometric, but it is alternating, right? The natural log term downstairs, there's nothing being raised to the n downstairs. This cannot be written as like sigma r to the n. So it's not geometric, but it is alternating. So the alternating series test is the way to go. I changed pens, didn't I? So I'll use AST. AST says I need to look at the BNs. So here BN is just the non-alternating part of the ANs, the part that doesn't flip back and forth with sign. And I need to answer two questions. Is the sequence Bn decreasing? And is the limit of the Bn's equal to 0? You can recognize that AST is a good idea here because the series alternates. That's why I wrote out the first few terms. It goes positive, negative, positive, negative, positive, negative. Every other term changes sign, so the series is an alternating series. With any alternating series, it's worthwhile to take a look at what AST says. So in other words, the -1 to the n is what tells me to use AST here. So are the BNs decreasing? Yes. Natural log of n is increasing. Picture the graph of the natural log function. Natural log of n is dots along that graph. So the dots keep getting bigger and bigger and bigger along natural log of n, which means the reciprocal, which is 1 over the natural log of n, which is Bn, is the reciprocal of an increasing sequence, which means it's decreasing. An alternate attack to show that the BNs here are decreasing would be to show that the function f of x equals 1 over the natural log of x has negative derivative. So an alternate attack here has f primed of x negative for all x bigger than 2, or at least eventually. But I try to avoid derivative work in these problems wherever I can because it takes a while, right? It's a quotient rule derivative, it's not pleasant, and then you have to solve the nonlinear inequality. It's more work. So if your thing that you're trying to show is decreasing is a straight up reciprocal, 1 over some shit, show that that's decreasing by showing that the shit downstairs is increasing. Here, showing that natural log n is increasing, this is obvious. I am okay with a Calc 2 student saying natural log n is obviously increasing. It's something you should definitely know because you know the graph of the natural log function. You know the derivative of the natural log is 1 over x. So that's always positive as long as x is positive. It's like, it's no work. All right, so this is how I would do that part. And then the limit of the BNs, yes, this limit is 0 because lim n to infinity 1 over the natural log of n is 1 over the natural log of infinity. The natural log of infinity is infinity, so that's 1 over infinity. That's 0. Therefore, by the alternating series test, the series S converges. But I don't yet know whether S converges absolutely or conditionally. Remember, all series fall into one of those 3 buckets: absolutely convergent, conditionally convergent, or divergent. There's no in between. Every series lives in one of those. So here, all I've discovered is that S does not diverge. But I still don't know between the conditional convergence and absolute convergence which bucket it falls into. So what should I go on to do next? How do I determine whether this convergence is absolute or conditional? That's the question. So S does converge, but is the convergence absolute or conditional? Here we need the definition. So S being absolutely convergent would mean that the series I get by swapping AN for its absolute value converges. So we need to check. The question is, does it? So if this series converges, then S converges absolutely. If this series here diverges, then S converges conditionally, because we already know that S converges. The question is now, does the absolute value series for S converge? If the absolute value series converges, then the convergence is absolute. If the absolute value series diverges, then the convergence is conditional, because I already know that S converges. And the question is now, what about the absolute value series? What sort of tests could I use for this guy? So the absolute value series here, absolute -1 to the n over the natural log of n. I will clean him up algebraically. That is the sum from 2 to infinity of the absolute value of -1 to the n over the natural log of n. This is the same as sigma n from 2 to infinity 1 over the natural log of n. So does that series converge or diverge? What sort of tests could I use for him? Maybe it would help if I write out the first few terms. So this is 1 over natural log of 2 plus 1 over the natural log of 3 plus 1 over the natural log of 4 and so on. Does it pass TFD? My chat is being shitty. Sorry, I guess you guys are probably answering and I just can't see it. Yeah, no, sorry, I can't. My chat's supposed to be like blinking red every time I get a message, but it's not doing it for some reason. So I'm going to go back here to 1223. Tells AST, we answered that. Absolute value of the inside, good. See if it's still convergent, good. No, I couldn't, but I see it now. Ratio test, TFD, DCT. I see 3 suggestions. So I asked whether TFD would work here. TFD is inconclusive here. As n goes to infinity, the natural log of n goes to infinity. 1 over infinity is 0. So this will not fall to TFD. TFD here, I'll write it out just. Oh, equals 1 over infinity equals 0. So TFD is inconclusive. The ratio test here would be a little bit tricky, actually, because you'd have to take the limit as n goes to infinity, log n plus 1 over log n. That limit does turn out to be 1, so ratio test is also inconclusive here. But Ryan nailed it. DCT will do the job here. The natural log of n is smaller than n itself. All right, if you take a number and you take the log, as long as that number is bigger than 1, the log will be smaller. This implies that 1 over n is smaller than 1 over the natural log of n. Smaller denominator on the right, bigger overall. And of course, as long as n is positive, these things are positive. So my series, the absolute value series here we're playing with, find some paper, I can continue this on. Ah, fuck it, we'll just squeeze it here. Okay, so therefore, because sigma 1 over n diverges, this inequality shows sigma 1 over log n diverges by dct. There it is. All right. So my series, sigma 1 over log n, this guy, is made up of terms that are a little bit bigger than the harmonic series, sigma 1 over n. So by direct comparison to the harmonic series, the absolute value series here is divergent. So the series S is convergent, but not absolutely convergent, i.e. S is conditionally convergent. Feel good? I'll be mindful here to keep reopening the chat. Yeah, so DCT is the way to go here. You could have also used the integral test, but the integral of 1 over log x is actually kind of nasty. Kind of nasty is an understatement. The integral of 1 over log x is horrible. We want to see this again. So I'm curious about whether or not my absolute value series converges or not. So I simplify it. It simplifies to the sum from 2 to infinity, 1 over the natural log of n, which has first two terms looking like this. 1 over the natural log of n is bigger than 1 over n because the natural log of n is smaller than n. This is a perfect direct comparison inequality showing that the terms of my series are a little bit bigger than the terms of the harmonic series. I know that the harmonic series diverges, so this inequality, I abbreviate INEQ, this inequality shows that my series, the 1 over log n series, diverges by direct comparison. Which means S, well, convergent by AST is not absolutely convergent. So S is conditionally convergent. Okay. How do you know which test to use is a good question? And that's really the hard question. And the answer is, it's a lot like, how do you know which integration method to use? Practice. You must practice. Okay, you can always take your time and run through every single test until you find one that works. The trick is knowing the hypotheses to the test. So what needs to be true about the series in order to apply the test. I know I shouldn't fuck around with the integral test on the original series here because the terms of the original series aren't all positive. Similarly, I know I can't start here with a direct comparison. I can't do any of those things because all of the series tests I have from 11.1 through 11.4 require the terms to all be positive. The terms of this series are not all positive. In fact, they alternate from positive to negative to positive to negative. That tells me, boom, AST. In general though, the answer to your question is hard. How do you know which test to use? Practice. Just like how do you know which integration method to use? You get a feel for what kind of series play nice with what kind of tests. So the series T. The test I want to use here is going to be the root test, because the nth root of this stuff is nice, because it's all being raised to the nth power. If this stuff inside here was constant, then this would be a geometric series. But it's not constant, it's got n's in it. So if you have a bunch of stuff raised to the n, then the root test is a nice way to go. L is the limit as n goes to infinity of the nth root of the absolute value of an, which here is the limit as n goes to infinity of the nth root of the absolute value of 1 minus n over 2 plus 3n all raised to the n, all inside absolute values, all under the nth root. So when do you use the root test? You use the root test when your series has a bunch of stuff all raised to the n, because the nth root and the nth power will cancel. So equals dot 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 equals lim n to infinity. The nth root and the nth power cancel, and so you just get absolute value 1 minus n over 2 plus 3n. Now, what is this limit? Remember, the absolute value is a continuous function, so I can shove my limit inside. What is the limit inside here? What does this piece go to as n goes to infinity? Renormalization will work, but you shouldn't need it at this point. We should be getting good. Fastest growing term upstairs is the negative n. Fastest growing term downstairs is the 3n. So if you were to renormalize, this would be 1 over n minus 1 divided by 2 over n plus 3. So this limit inside the absolute value is negative 1/3. The absolute value of negative 1/3 is positive 1/3. Period. Since L is 1/3 is less than 1, the series T converges absolutely by the root test. This is one of the reasons the root and ratio test are so dope. They don't just tell you whether your series converges or diverges, they tell you whether your series converges absolutely or diverges. So the fact that you get the absolute convergence for free is really, really nice. So T converges absolutely. So this, I'll put it here maybe, conditionally. This guy converges absolutely. Any ideas? So first, questions on the argument here showing that T converges absolutely. This is our first root test example. I'll double check the chat real quick. I wish this would stop going away. Integral of 1 over x, and I'm scared. Yeah, so coming back to Dalton, the integral of 1 over the natural log of x is straight up not doable by hand. It's one of those functions like e to the negative x squared or sine x over x, where you cannot find a closed form antiderivative. You should be afraid of that integral. It's fucking terrifying. However, you could show that the integral 1 over ln x from 2 to infinity diverges by using a comparison test for improper integrals, the same way we used the direct comparison test for the series 1 over log n. Fernando asks, did I think of the growth rate rules to come up with the inequality I used to show that 1 over n is smaller than 1 over log n? Not really. So the growth rate rules are about limits. And here, it's just a fact that the natural log is smaller than his input. If you graph y equals x and y equals natural log x on the same coordinate axes, y equals x is always above y equals natural log x. So it's a slightly more fundamental thing than growth rates. It was a little bit more straightforward than that, but I suppose you could also think of it in similar terms. But the natural log of some number is always smaller than the number itself. When we see a nice function, easy to take the integral, we should try integral test first. Caesar asks, if the integral is not bad, should we always do that first? I would say not necessarily, Caesar, because the integral test requires you to go through that process where you show that the corresponding function is positive, continuous, and decreasing, and then you do an improper integral. It kind of takes forever. So even if I see something I know how to integrate, I don't like to jump straight to the integral test. I still want to ask, is there something lazier that I could do? Because I don't want to have to spend that time showing continuous positive decreasing all the time. But if you recognize that the function is easy to integrate, then you should keep the integral test in your mind as a possibility. A lot of folks helping me out with that limit. I appreciate it. Yep, the inside goes to negative 1/3, so the whole thing goes to positive 1/3. Mariano, why did you use negative n instead of 3n? I'm not sure where we're looking. So an here is 1 minus n over 2 plus 3n, all raised to the n. So upstairs, I've got 1 minus n. Downstairs, I've got 2 plus 3n. So if you were to renormalize, if we want to look at the details here, we can do it. No harm in that. So this is something we want to get to a place where we're fast at it. Right here, this is equal to lim n to infinity 1 minus n over 2 plus 3n. And I'm going to multiply top and bottom by 1 over n. I'm going to divide out by the fastest growing term. If I distribute my 1 over n upstairs, I get 1 over n minus 1. And downstairs, I get 2 over n plus 3. So now as n goes to infinity, 1 over n goes to 0. So my top is 0 minus 1. And downstairs, 2 over n goes to 0. I get 0 plus 3. That's negative 1 over 3. Oh, like that. Nicholas, I'll ask you to send me an email for that one, buddy, and I will try to find some time tomorrow. I do think I can. Yeah, I just have to make sure it lines up with the rest of the stuff in my schedule. I'll find a time. The limit part. So Mariana, are you comfortable with this limit now? Is everybody comfy with this limit? So the stuff inside the absolute value goes to negative 1/3. So the whole thing goes to positive 1/3. Okay, Nick, yeah, I'm sorry. I'm just a little bit behind on my email. I will be getting to those messages this afternoon, and I'll send you a reply. Gustavo asks, could we use the limit comparison test for t? I think you probably could, but it's not going to be super clean. I think the choice for limit comparison here would have to be So if you wanted to use LCT, pick Bn equals -1/3 to the n. So then the limit as n goes to infinity of an over bn would be the limit as n goes to infinity 1 minus n over 2 plus 3n to the n divided by -1/3 to the n. And you would have quite a bit of work to do. I don't think this is at all an easy limit, but it would come out to 1. Right? I can see that this limit down here is going to come out to 1, but it's not going to be an easy thing to show. And I wouldn't recommend attacking the problem with limit comparison. Because the whole series here, because everything inside the sigma is raised to the n, this is screaming for us to use the root test. So we did the exact correct thing here. I wouldn't change a thing. You could use LCT, but it's not going to be super easy. Whereas the root test limit here is super easy. We've talked about it for quite a while, so maybe it's starting to feel daunting. But in truth, this is a very straightforward, very fast limit. All right, the nth root and the nth power cancel. What's left is a linear over linear thing. That's something that we've been handling for a long time. So the root test is the ideal attack. Also, LCT would not give you absolute convergence. It would only show you that the series converged. So then you would have to come back and do something else for absolute convergence. And that something else is necessarily, I think, going to be the root test. So my recommendation is definitely to do just what we did here. So T is resolved. T converges absolutely. How about Q? So I'm going to write Q down. Okay. Any ideas how I can approach this series? I'm doing for time. We're getting close here, so it's alternating. The -1 to the n makes it alternate. The n squared downstairs kind of makes me think P series a little bit, but it's not a P series because there's all this other shit going on. But the downstairs being n squared kind of makes me think of P series. The inverse tangent of n, this piece is bounded between pi over 4 and pi over 2. The arctan of 1 is pi over 4. Arctan increases from there, and its upper bound is pi over 2 because of that horizontal asymptote. So when I see this, what I think is, and I'll say recall, lim n to infinity tan inverse n is pi over 2. So when I see this piece here, I kind of just think of him as like stuff that's close to pi over 2. Essentially constant. He does not go off to infinity. He does not go off to 0. So he's not really doing much. The inverse tangent of n here really doesn't do much. So the series, his convergence behavior is coming from the -1 to the n and the n squared. I can't use a direct comparison. I can try the test for divergence, but it won't help because the limit as n goes to infinity of an is the limit as n goes to infinity of -1 to the n inverse tangent of n over n squared. This limit is going to be 0. The -1 to the n piece bounces back and forth. So the limit is actually kind of hard to take, right? But that's lim n to infinity -1 to the n times pi over 2 all divided by n squared. So this the negative 1 to the n makes you bounce back and forth from positive to negative, but the n squared downstairs goes to infinity. So this is actually 0. The arctan just goes to pi over 2. So that's inconclusive. I'll spoil it for you. The ratio test and root test are both inconclusive as well. The ratio test is inconclusive because of the, because if you take that limit, the an plus 1 over an limit here will go to 1. The root test is also inconclusive. But what will work is thinking about absolute convergence. Remember, abs convergence means that the absolute value series converges. And if I take absolute value, then I can use DCT because then everything inside will become positive. So sigma absolute value negative 1 to the n arctan n over n squared is equal to sigma n from 1 to infinity absolute value of negative 1 to the n. The inverse tangent function here is positive, so the absolute value of him will just end up being him, but I'll write it all out just because we're still getting used to this. This piece is 1. This piece is just arctan n because the absolute value of something positive is just that thing. This piece is just n squared. So this is sigma n from 1 to infinity inverse tangent of n over n squared. And I can use DCT on this. I can't use DCT on the original, but I can use DCT on this. Monotonicity is not a property of series, it's a property of sequences. So Lucas asked, can a series be monotone? There might be ways you could discuss that, but it's not something that we've defined. You could use the alternating series test here, that is correct. But first, showing that this sequence is decreasing is going to be a pain in the ass because it involves the derivative of the inverse tangent function, which isn't fun. You could use limit comparison here. Limit comparison not on the original, mind you. Can't use limit comparison on Q, but you can use limit comparison on the absolute value series. So the big step here is to, instead of trying to answer convergence and then absolute convergence, jump straight to absolute convergence. By jumping straight to the absolute convergence, I make the inside of the series positive, and now I can use all my comparison tests. I can use whatever I want on this guy. And while a limit comparison would work, a direct comparison is easier. So DCT on this guy, you observe that your series is actually smaller than this guy. Because remember, arctan is always smaller than pi over 2. He increases monotonically to pi over 2. So while the series isn't monotone, I think maybe that's what Lucas is getting at. The sequence that makes it up is, at least the numerator is. It's true that if I found that the absolute value series diverged, I really wouldn't learn anything. I couldn't conclude that the original diverges, it would be a total flop. So jumping to absolute convergence is something that you want to do if your series doesn't have positive terms, you can't use the tests you want, but you strongly suspect that your series converges absolutely. And that's what I was getting at when I said this thing kind of looks like a piece series. Like if you forget about the numerator, 1 over n squared is a convergent piece series. Okay, well, I've slapped a negative 1 to the n on. That makes it alternate, which makes it converge even easier. And then the slapping on the arctan really doesn't do shit because arctan is always bounded between 1 or between pi over 4 and pi over 2. So really, in the back of my mind, when I look at this series, I'm thinking this is an even nicer form of the 1 over n squared series. It's not nicer algebraically, but as far as convergence is concerned, it is nicer. So I take absolute values inside the series, and I get this. And this guy I can show to converge using the direct comparison test. So I have this inequality. Moreover, sigma n from 1 to infinity pi over 2 divided by n squared is pi over 2 sigma n from 1 to infinity 1 over n squared is a multiple of a convergent p-series. Here p is equal to 2, which is bigger than 1. Thus, by my inequality, I'll call it star, and dct, what is true? This series converges. I'll call it Q prime. Q prime converges, which means Q converges absolutely. Cool shit, right? So some series, specifically series that look a lot like series you know well, but for whatever reason don't have all positive terms, for series like that, some series are easiest to work with by first taking absolute values inside. That will make all the terms positive. So then you can use all of the tests from 11.1 through 11.4 without fear. While this is an alternating series, my original here, Q, is an alternating series, it would be a pain in the ass to use AST because showing that inverse tan n over n squared is decreasing is going to involve some nasty, nasty derivative work. It's not a straightforward reciprocal. And at the end of all your alternating series test work, all you would get is that Q converges. You still wouldn't know whether the convergence is absolute or conditional. So you would still need to go back and do this. So why not just do this first? Questions on the series Q? Jumping straight to absolute convergence is a good idea if you think you can show that the absolute value series converges, especially if you think you can show that quickly. So time is one of the struggles here. And it's something that you'll get better with as you practice more. So all of the algebra and calculus that you guys have taken up to this point is supposed to imbue you with some intuition for functions like arctan. So being able to spot that the arctan here really doesn't fuck with shit very much is really the big thing. And you've heard me say this a few times about the inverse tangent function, that it's one of those ultra important guys. Natural log functions, sine functions, you want to have that level of intuition for all of these. But the more you practice, the easier it will become. And my recommendation is that between now and Friday, I would burn all the time you have on practicing this stuff. And make sure you're communicating with each other. I haven't checked out that Discord since whatever, last Thursday, but make sure you're communicating with each other and asking questions and talking. I don't know if Dumbledore knew a whole lot about infinite series, but I appreciate the comparison. That's very cute. Okay, so Q is absolutely convergent. I think we're getting a little short on time. I want to make sure that we do a ratio test example, and R is not a ratio test problem. So I'm going to skip over R. I'll let you guys work on this. You could start with AST. Your BNs here are 1 over n log n. That is a straight reciprocal, so you could show that he is convergent fairly easily using AST. to get absolute convergence here will require a little bit more, but I do think, actually I don't remember. Oh, that makes it more fun to leave it to you guys. Okay, so this converges by AST, but I'll leave the absolute convergence question up to you. That's gonna be an integral test. I'm pretty sure you need the integral test there. Although you might try a limit comparison for the absolute convergence thing. So for R converges by AST. And then the series, I used the prime notation before, so I'll use it again here. Sum from 2 to infinity abs, -1 to the n over n log n. This is really just the sum of 1 over n log n. You could try the integral test there. That will definitely work. You might be able to get away with limit comparison. So try IT and LCT with Bn equals 1 over n. I actually think this diverges. The more that I think about it, I'm pretty sure that that's a divergent series. And I think limit comparison might be faster than integral test. But I'll let you guys sort out the last little bit for R. Last part for Q. Here we go. And then before we go, we do need to practice with the ratio test a little bit. So I used the prime notation here to talk about the series that you get when you swap in the absolute value. And that's why I used that same notation here. So I'm just using the prime to refer to the associated series with the inside replaced by his absolute value. It's not the same as the original, so I can't call it R, but it's definitely closely related to R, so I just had to pick a notation, and that was what I chose. Calling it absolute value of R would be wrong, because that would mean absolute value is on the outside of the series, not on the inside. It's tough to pick a notation for that. But because I called the previous one Q prime when I swapped in the absolute value, I chose to call this R prime. It doesn't matter. You could eschew the labeling altogether if you wanted. Okay. So I'll leave this right here in case anyone is still working, but we do need to practice at least 1 or 2 ratio test problems. And it should involve some factorials. Anytime you see a series with factorials, ratio test should be your first thought. Right, so for these 2 new tests, how do you spot what test to use? That's a big question in the back of our minds all the time. If you've got a bunch of stuff raised to the n, try the root test. If you've got factorials, try the ratio test. Those are the basics. So ratio test says calculate L as the limit n goes to infinity, absolute an plus 1 over an. So this is limit n to infinity, absolute value. An plus 1 is -1 to the n plus 1 over n plus 1, all factorial. And it's important that you use the parentheses like this, right? With the n plus 1 in parens and then the factorial on the outside. So an plus 1 is always what you get by swapping n with n plus 1 in parens. If you want to be real careful, you could write it like this. But remember those parentheses. Those parentheses are algebraically crucial. If you forget them, it'll fuck shit up, I promise. We need to then divide all of this by an. An is -1 to the n over n factorial. And all of that is in absolute values. All right, I am going to pull this stuff off now. So here I get lim n to infinity, -1 to the n plus 1 over n plus 1 factorial. I'm just going to flip and multiply by the bottom. That's n factorial over -1 to the n. And then I like to group things together. I'm multiplying two fractions, so I can, you know, I don't have to worry about common denominators or any of that stuff, but I'll put the -1 to the n stuff and the n factorial stuff together. So I get lim n to infinity absolute -1 to the n plus 1 over -1 to the n times n factorial over n plus 1 factorial. All in absolute values. Don't forget the absolute values, they're important. -1 to the n plus 1 divided by -1 to the n is -1 to the 1. N plus 1 copies upstairs, n copies downstairs, cancel all except for 1. And then I write out the factorials. N factorial is n times n minus 1 times n minus 2 all the way down to 3 times 2 times 1. N plus 1 factorial is n plus 1 times n minus 1 times n minus 2 all the way down to 3 times 2 times 1. We've talked about this before. A bigger number factorial contains all the factorials of the smaller, of any number smaller than him. So hiding inside of n plus 1 factorial is a copy of n factorial. The n's cancel, n minus 1's cancel, n minus 2's cancel. All this shit cancels. So what's left is the limit as n goes to infinity of the absolute value of -1 times 1 over n plus 1. What's up, baby? Oh, I don't know it. No. If you got just a second, I can probably pull it up. Okay, so my last step here, guys, is to split the absolute value. I get absolute value of -1 times absolute value of 1 over n plus 1. This piece is just 1. So this is the limit as n goes to infinity of 1 over n plus 1, because this guy is positive. So I can get rid of the absolute values. That's 1 over infinity, that's 0. So L is equal to 0, which is less than 1. Therefore, my series converges absolutely. I think we are probably real close to being out of time, if not out of time altogether. So on the way out the door, I got one more for you. Try the ratio test on sigma n from 1 to infinity n factorial over n to the n, and sigma n from 1 to infinity n to the n over n factorial. These are two popular series to stretch your ratio test legs, and these will both require that special e to the ab limit that we talked about at the start of class. Okay, that's section 11.6. Absolute convergence and convergence, how they relate to one another, the theorems, and the two big tests, root test and ratio test. On Wednesday, we're going to solve lots of problems. I'll do whatever problems you guys want. So make sure to come prepared with questions to ask on Wednesday. Friday is going to be our test. The test will be in Canvas and it will be run the same way that test 1 was run. So there will be 2 assignments in Canvas. One will say exam 2, take questions, take the test here. That's where you'll go to take the test. It'll be proctored by HonorLock. There will be some true, false, and multiple choice and some free response. I think I'm going to weight the test a little bit more towards free response this time because I've had some feedback on the true, false, and multiple choice portions, and I agree with that feedback that there's a little bit of ruthlessness there, and I'm not trying to be ruthless. But you need to work hard. You need to be grinding real hard right now. So sink 3 more hours into this stuff today. Sink 3 hours into it tomorrow. And then on Wednesday, come with questions. After class on Wednesday, same shit. 3-4 hours, 3-4 hours on Thursday, and you'll be all right. Okay, if you do that, you'll be all right. But if you don't, then this is gonna be brutal. I don't want it to be brutal for you, but a test has to be a test. So please prepare hard. Don't forget the early stuff. Don't forget how to do improper integrals. Don't forget the theorems that we talked about at the beginning of 11.2, definition of partial sums, telescoping series. Look in the modules section on Canvas. I have posted some fresh stuff there for you guys. And that is it. All right, so I'll see y'all on Wednesday. I'm gonna switch over to my office hour now. If you wanna solve more problems, come meet me there. And then review Wednesday, test Friday, okay? To study for the multiple choice and the true-false, make sure you know the theorems well. Make sure you know the hypotheses and the conclusions. So most of my tricky true-false and multiple choice questions for exam 2 are like true-false. If limit n to infinity an equals 0, then series sigma an converges. False, right? Because that's the converse to TFD. And if you know TFD well, then you know that that is false. So that sort of thing. Make sure you know the theorems well. There is a section in the textbook. I'll switch my screen share back on. So I want to answer this question well. Ryan asked, how do we study for the true, false, and multiple choice stuff? Dig it. Go to chapter 11. There's a whole bunch of shit here. This review is a good review. It's got challenging true, false questions. It's got lots of good multiple choice questions. It's got lots of stuff to practice. So if you finish the study guide and the homework, this would be where I would go next. Get into the textbook, work review problems there. They're all good. You won't be able to do anything that has to do with power series or Maclaurin series. Ignore those. But everything else you can do. Right? So remember, our test goes through section 11.6, 11.7 technically. All right, that's it. Going over to office hour now. If you want to talk more, meet me there. Otherwise, hope you guys have a good afternoon, and I'll see you on Wednesday.